Well, once again, welcome all to you of joining us today, especially those connecting from across Latin America and Caribbean. On behalf of the UN Big Data Regional Hub in Brazil, the FAO, and the task team on Earth observation, it's a pleasure to have you here. We are very excited to start another round of learning and collaboration together. This workshop is the ongoing capacity building effort to improve how we use Earth observation and artificial intelligence to agricultural statistics. We're building the success of the FAO and EUSTAT program already implemented in more than 25 countries. The goal is to give you both foundational knowledge and practical tools we've learned by doing so you can understand better how to use those technologies in your countries and institutes. We during this week we will have a mix of live sessions and self-paced activities. So for the days we're not online, we share the concept, which we have two links on that: the handbook of sensing and the guide on satellite images series. Uh, just another quick reminder to receive a certificate. Participants to attend at least 80% of the sessions. Okay. Um, so I really encourage you to participate actively on the questions and answers experience we have at the end. This is a space co-learning, in, and it's my pleasure to introduce who has been a key partner in this initiative and who many of you already know, which is the Dr. Lorenzo de Simon from NGO, who will open the workshop with an overview of EO and I applications on agricultural statistics. Mr. Lorenzo, morning again. The floor is yours, okay?
Thank you very much, Paulo, and good morning to the colleagues in the Latin American Caribbeans. It's a pleasure and an honor to be here and to collaborate for this capacity building event. So I would like to share my screen. Let's see if I successfully do that. No, this is just a second. Just a second. Uh-huh. Okay. Okay. Okay, just a second. Okay. Okay. I need to share screen here. Okay. Can you confirm that you can see my my screen, please? Paolo, can you see my screen?
Okay.
Yeah.
Okay, thank you very much. So today we're going to have almost 2 hours together. So I'm going to try to make good use of our time. We will start with an overview of Earth observation and artificial intelligence applications for agricultural statistics. In particularly, we're going to have a brief introduction to the Earth observation as a technical domain. Then going to the relevance of why AI and Earth observation are useful for agricultural statistics, provide some use cases, so how they are currently applied, which are the key areas, and then just to remind ourselves of the importance of accuracy, validation, and assessment of the bias, and then some conclusions and takeaways. First of all, we know what are satellites. So we have sensors mounted on satellites orbiting Earth or geostationary. We refer to most orbiting, let's say, satellites like Sentinel, Landsat, MODIS, which observe our planet regularly. They can measure crop growth, they can measure land use change, droughts, and etc. And they are consistent over time and unbiased, of course, unless some accidents happen to the satellites, like like it can happen. So just as an example, we have Sentinel-2 data, which has been operational since 2015. It's managed by the European Space Agency. It has 13 bands. It's an optical sensor. It has a 290 kilometers width, so its stripe is very large. Every 5 days, it's revisiting almost every place on the planet. Not really, but more or less that's the average. It can allow for many applications like land cover mapping at 10 meters resolution, vegetation monitoring at 20 meters resolution. It also has a cloud detection band at 60 meters. And then we have the Landsat legacy. Now we know the Landsat 9 started in 2021, but Landsat 1 was launched in the 70s. So Landsat constitutes the largest legacy of remote sensing data. It works in 19 bands. It has a slightly smaller width compared to the Sentinel. It has a 16 days revisit time. The land cover mapping that it allows is really 30 meters resolution, as well as the vegetation monitoring. It has also thermal monitoring at 100 meters resolution, which is resampled at 30 meters resolution. And it has also cloud detection with Cirrus band. And of course, this is just some visualization of how NDVI, how vegetation is spotted by the Landsat data. So why are Earth observation and AI relevant for agricultural statistics? So I'm going to try to explain this with this very strange chart here. So those 4 graphs, basically, they show how different land cover types, for instance, avocado, banana, mango, guava, woody vegetation, bare soil, etc., how they reflect sunlight across Sentinel-2 spectral bands over 4 months. So you can see on the horizontal line, those are the different bands, and the reflectance is expressed as a percentage for each band. So what we see in those charts is that the reflectance from form seasonal patterns, and these spectral fingertips, they change over time. So for instance, guava, which is the light blue, it consistently has the highest reflectance in the near infrared bands. Built up, which is in orange, and bare soil, which is in gray, have a flatter, less green spectral curves, essentially. You can note also how vegetation reflects strongly in the near infrared around the now narrow near infrared band. So all these are essentially what artificial intelligence models use to distinguish crops like avocado, mango, guava from each other and from non-crop areas like bare soil or water bodies. So the key points is that each crop has a unique reflectance curve, which can be detected by time series Earth observation data. Temporal dynamics help to distinguish crops, and AI can basically automatize the discrimination of those characteristics and the production of crop maps. And then from the crop maps, essentially, we will see how we can extract statistics. So some common applications, of course, of remote sensing in agriculture you will have already heard of and you probably are working on is crop type mapping, crop area estimation, crop yield forecasting, crop health monitoring, crop suitability analysis, drought and flood monitoring, land use and land cover change essential analysis. So if we just look at a small example from Zimbabwe, if we start from a generic land cover map, then we can zoom in the agricultural class, and we can then start to use AI and remote sensing to process segments. So segmentation of the which allows to map the boundaries of each plot. And then when we integrate this with time series analysis, then we can distinguish between the crop types. And of course, this already is giving us a first indication of the area distribution. Furthermore, if we add additional geospatial data like on climate, on soil, and we input also the parameters of the crop growth model, then we can forecast also the crop yield in a geospatial explicit model, and then this can also be used to produce statistics. In addition to this, of course, we can also combine crop type mapping with the drought or with flood predictions, prediction mapping, and response. And so essentially we can overlay, for instance, flooded areas with the crop type data and with the plots. And essentially this allows us to assess what is the impact on production, but also which farmers have been impacted for other type of applications like subsidy and compensation systems. So what is in practice Earth observation and AI doing for agricultural statistics? Well, we can respond by assessing first the requirement, which is a growing demand for accurate, timely, and reliable data. And as we saw, Earth observation data provides consistent, repeatable observation at scale. AI allows for the automation and the extraction of patterns from massive Earth observation data. And finally, Earth observation, more in general, provide critical data for monitoring and achieving sustainable development goals, especially in agriculture, by enabling consistent, scalable, and timely information. If we look more into particular of use cases for Earth observation, thinking of the requirement of national statistics offices, we can identify some specific use cases which may resonate with your daily work. First of all, economic efficiency. So Earth observation data can be used in area estimation to maximize the accuracy of the statistics, meaning having lower variances, and to reduce the cost, because we don't need to intensify field sampling, but we just integrate additional data from free and open remote science data. Granularity. Often field sampling is designed for national level statistics. In these cases, Earth observation data can allow to disaggregate the area statistics at smaller administrative areas, provinces, counties, for instance. Timeliness, because statistics are usually, the official statistics are available at the end of the field campaign once in a year, sometimes even 6 months after the harvest. Using Earth observation data, we can basically forecast those statistics. We can have early estimation of areas, which of course will not substitute the official statistics, but can give an early signal. Earth observation data can also inform the sampling design. So it can allow us basically to implement area frames, to move from list point approaches. It can help us to define the optimal sample size and segment size, so it optimizes the sampling. And finally, we can use Earth observation data to assess the data quality of the database of field observations. Actually, we will see this very much in details also during this week. There's going to be specific session on how to use AI for improving the quality, checking the quality of field data. And finally, we also have other application of EO data. For instance, for SDG reporting, we have SDG 15, for instance, that can be reported using Earth observation data for the majority of the targets of the indicators, like 15.4.2 mountain green cover index. We also have components of SDG 2 that can be monitored using Earth observation, as well as specific indicators under SDG 6. And then we have, as we saw, also other applications like early warning, water body maps, soil suitability, and etc. But then the question is, how and where does the EO and I work actually together? So in order to elaborate on this, I'm using a slide that was originally prepared by Gilberto Camara, which is showing in a very simplified but very representative way the traditional foundation for land cover classification, land use classification, and in particular crop type mapping. So we have the Earth observation data cube, from which time series images are extracted. And then on the right-hand side on top, we have the field data collection, so the ground truthing data. And then in the middle, we have the training, which is really the algorithm, okay, where the classification is taking place. And essentially, artificial intelligence is really used at the level of of course, the creation of the time series analysis for gap filling, at the level of improving the quality of the samples, but of course in the training of the algorithm, so the choice of the algorithm. But today we're going to focus on two aspects. We're going to focus on the in situ data, and then we're going to focus on the model, on the training. So I'm just going to give some use cases on how EO and AI are improving the field, the in situ sector. So first of all, it helps us to select optimal sampling locations. How does it work? Essentially, we can use cropland and non-cropland mask to stratify the territory in different agricultural zones. And then AI algorithms can help to select optimal representative sampling points based on probabilistic sampling, where in situ crop measurements are most needed. And this can improve the design of surveys and ensure unbiased and efficient ground collection. The benefits, of course, are higher statistical precision with fewer field visits. It reduces the travel cost for survey teams and increases coverage of rare and heterogeneous crops. This is an example of how this was applied by Zimstat, so Statistics in Zimbabwe. Essentially, at the beginning, we merged the Zimbabwe national boundaries with the World Cover 2022. It's a global land cover map because Zimbabwe did not have its own national land cover map at that time. And then we create an area frame covering the entire country of Zimbabwe, and the grid is 2 by 2 kilometers cell size. And from the world cover, we extract the cropland mask. So as you can see in red there, that's just the area where agriculture is detected from the global uncover map. And then within each cell, that's the image B on the right, we basically assess the ratio between the area colored in red by the total area of that single square. And so we measure agricultural intensity. And then we can basically stratify our pixels, our cells actually, our primary sampling units by strata, by agricultural intensity. Then we use AI to compute the sample numbers, the optimal sample numbers using Cochrane's formula. And then we allocate randomly the PSU across, so primary sampling unit across each strata. And then we do the random allocation of 15 secondary sampling units for each primary sampling unit. And the secondary sampling unit, of course, is then the size of the pixel of the sentinel pixel, 10 by 10. So this is one way to use EO and artificial intelligence to inform survey design. Another example is instead using AI to derive field boundaries to guide surveys and censuses. So how it works, very simply, you have Sentinel data, you have Landsat data, and then there is an AI segmentation, which basically automatically maps all the boundaries, all the crop boundaries. These field boundary maps are then loaded into enumerators tablets during the agricultural survey or the census, so that when the census is taking place or the survey, instead of walking the whole field with the GPS, the surveyors, they can georeference the parcel directly on the tablet, talking to the farmers. So they establish a connection between the questionnaire and the parcel. So basically the georeferencing is happening without having to walk to each plots. And this can save a lot of time. So it reduces error, and it assures the complete coverage of smallholder fields, avoiding biases. And I want to mention that, for example, IBGE, Brazil, so they are already using this approach. So they're using AI and satellite data in order to prepare the boundaries, okay, to support the Census of Agriculture for 2026. Of course, it's a large project, and the target is to have over 1 million plots by June, and more than 50 cities fully mapped, representing diverse landscape, biomes, agricultural holdings, among other factors. And of course, credits to Jan Nunes for this work that has shared prior to this presentation today. And the third example I wanted to give was really to how we use EO data and AI to assess the quality of in situ data. And of course, We have many criteria to assess the quality of in situ data. Some of them refer to the completeness of the information, including rich labels linked with geospatial features, the topology, the metadata completeness. But I really want to focus on the last three, let's say, criteria, which are the following: geospatial feature GPS coordinates accuracy visually checked using most synchronous Earth observation imagery, sample purity based on multispectral reflectance heterogeneity assessment, and labeling quality based on NDVI time series clustering and profile similarity. And of course, AI can help us in the especially on the last two, let's say, aspects, because the first one is more of a visual inspector from the expert. So let me give you an example. Those are polygons of crop plots georeferenced in Rwanda by the enumerators. And of course, when we compare those ones with Google imagery, we can see that there are problems in alignments. But this is really a random check that is doing by the operator visually. In the next slide, instead, we go to the second step. So essentially, is the purity of samples. Now, you can see in the image here, we have basically a cloud-free planet base map on the left, and very high resolution imagery in the middle. And it's overlaid with a point observation expected to be a representative of a circle, so a radius of 20 meters. And you can see that the plots expected, the plots on the right highlights expected and unexpected NDVI profiles, and the associated standard deviation from a homogeneous wheat field derived from the Sentinel time series during the surveyed season. So you can see how basically we can use this type of inspection, which can be automatized, to discard, let's say, signatures which basically don't follow the expected profile. So it's indicating that we have a problem in that location. And again, we can see, like this is the third example, we can see we assume that crops have an homogeneous signature in the same agroecological zone where they are cropped. However, this is not always the case, and this needs to be this basically needs to be checked. So what we see here is basically the NDVI temporal profiles interpolated from cloud-free Sentinel-2 multispectral images acquired along the observation period in Ethiopia. And each color curve corresponds to a sample for a given crop. While basically the black curve is the average NDVI value of all samples for that crop. So we have in blue, we have the teff, in red, we have the wheat, barley is light green, peas are pink, and fava beans are orange, and maize is dark green. And essentially, we can see that the cycles are very diverse. And you can see that the temporal profiles, they show outliers indicating marginal sample quality. The different NDVI profiles, basically, for maize, for example, they reveal that a significant portion underwent a double cropping cycle within the observation period. Since the first crop cycle delayed basically the planting, the sample population needs to be divided appropriately using clustering methods. But of course, it becomes difficult to work on this when we have thousands and thousands of data. So this is when AI comes into the picture. And we have examples of algorithms like self-organizing maps, which, for instance, INE Chile is already using, which allows to carry out this type of investigation on the quality of the samples. So, for instance, those are the samples that have been used by INE within a crop type mapping, land cover mapping exercise. And the sum is basically clustering this data through a specific approach called neurons, and essentially is clustering together those pixels within neurons, which basically have a specific label, and then it's assessing if topologically speaking, those neurons are contiguous to each other. So in other words, this is what you get, is that you manage to group together the pixels within the NDVI, let's say, space. And what you expect here is to see neurons of the same color, of the same type, to be clustered together. And instead, you would consider outliers, those neurons which basically are surrounded by different clusters. So for instance, if you see on the top right here, you have this pink cluster, which is forage, and is surrounded essentially by deciduous fruit trees, and is surrounded by two late season cereal. So very likely that neuron is representing pixels which are outliers, and so on. You can see also here other examples of isolated neurons. And what this system does allows you to automatically detect within your training data those sampling data sets which should be probably removed, those ones which are instead consistent, and those ones where you should analyze further to assess the quality. The good thing is that on day 3 of the webinar, Professor Gilberto Camara and Estefania Pizarro from INA, they will provide a detailed presentation on the methodology to apply AI and Earth observation time series to automatically clean your training data and even to enhance it, so to artificially augment this data set. So the second area now where AI can help is really how we train the algorithm, the choice of the algorithm, of course, and so the classification approach. So I just wanted to recollect very briefly what is the typical approach in the supervised world. Essentially, we identify a study area, we conduct a field survey, which is possibly probabilistically, so that it has a statistical design. And then what we do, we acquire the satellite images over the area. The satellite images are pre-processed, and eventually they're transformed into a regularized data cube. And then what we do, we extract the spectral characteristics in correspondence of our sampling locations, which have been colored in red and in green because they are divided then for training and validation. But we associate the spectral characteristics coming from the data cube with the location of each sample, where we have also collected the label, so the crop type. So those labels then, together with all of the attributes, they are fed to a classification algorithm, which are where we have many of those. So for instance, we have a random forest. Once the random forest is trained, and so it understands what crops look like from the spectral point of view, then it's able to operate the reclassification of the satellite image. So every pixel is then going to be reclassified to the crop type map, which is more likely to belong to. So this is the traditional way to work with this. And of course, we have convolutional neural networks, random forest, temporal convolutional neural networks. Those are all machine learning approaches which fall under the big family of artificial intelligence. They require the labeled data. They may work without the information on time, so they can be detached by the temporal sequence, but we do advise instead to use models that consider the temporal sequence, like for instance, temporal CNN. So the strength of those models is really interpretability, because we can really understand which features are more important. For instance, the random forest. So it's very transparent. They perform quite well on large data sets. They can handle very well outliers, collinearity. And as mentioned, CNN handles very well spatial pattern, and temporal CNN adds time series modeling. However, we have a weakness in those models. So the weakness is really dependency on the labels. which are, of course, costly to acquire because they require ground truthing and field survey. There is also limited generalization of those models if the training data is small or is underrepresentative. And they come also with computational costs, specifically deep CNN. They require significant resources. Common use cases, historical and near real-time crop classifications with training data, of course. National, I would say, to medium and small scale studies. So to map crops, let's say at national level, but it already becomes more complicated if you want to map at regional level. So some examples, this is a project in collaboration with DANE Colombia and FAO, where there's been the land cover mapping of the meta department using random forest, rice mapping, and palm oil mapping for the meta department 2024. Furthermore, temporal CNN, which have been applied within another collaboration between FAO and Peru Midagri. So mapping at the farm-based level in the district of Jequetepeque in 2024, but also in other areas of the world. So for instance, in Zimbabwe, where Zimbabwe Statistics is using random forest to produce a national-wide crop mask and crop type map. And now we're thinking in how to operationalize this so that every season, there are 2 seasons in Zimbabwe, this is more or less automatically updated. And this is the last topic about models. And this is a bit more, let's say, what's coming up now, what's new on the market. And really, we're talking about pre-trained, self-supervised models like forma, like Presto. What are those? So they are self-supervised learning models which learn from unlabeled data by solving pretext tasks. For instance, predicting missing image patches. So we feed thousands of satellite images and we mask here and there pixels of the satellite image. And the task of the model is to recreate those pixels in those areas so that he learns all of the relationship between satellite data from multi-sources. So it is trained on satellite imagery, and then it's fine-tuned on smaller labeled data set. So when we want to then use it to forecast, then we have to train it on a smaller data set of labels, as we can see. We have examples of this. So there is the forma, which is transformer-based model for satellite image time series, which captures long-range temporal dependencies, which is important for crop phenology. Or we have the Presto, which is a newer model, which has been designed for multimodal Earth observation data, optical, SAR, digital elevation model, precipitation, and so on, or spatial patterns. And again, of course, they come with strengths and they come with weaknesses. So the strength is that they reduce the reliance on labeled data. So it leverages abundant unlabeled Earth observation data like global satellite archives. Transfer learning. So they adapt to downstream tasks. So crop yield prediction, for instance, with minimal fine tuning. And they have state-of-the-art architecture like transformers like Presto. They excel at modeling long-range dependencies, which are critical for crop cycles. However, there are also weaknesses in this. So first of all, computational complexity. So training transformers require significant resources. Interpretability and challenges, there's still some kind of black box nature compared to random forests. And then there is a problem with the data bias because performance depends on the pre-training data diversity. So for instance, Presto now is being used by the World Serial Team. This is a project funded by the European Space Agency, and it's been implemented by the consortium by Vito. And it's really this model, Presto, it has learned basically how to recognize cropland patterns from global satellite data without the needing to manually label for every image. And it can be used across several countries to save time and efforts. So we're thinking of countries who are missing their training data. So they want to rely on a global model. Of course, this is not the ideal situation. We would like countries to train their own models with with local data. Let's say the take-home message is that they learned data from itself, so no manual labeling. You can train it once on a large data set, and then you can use across countries with little or not, further training, essentially. And what the world serial is producing, thanks to this, is global maps of temporary crops, for instance, global maps of winter cereals, of spring cereals, and, for example, the maize fraction for the main season and the second season. And so when we look at them all together, of course, we can summarize, that the differences, between supervised and self-supervised. So, for instance, NADA needs supervised models. They need high quality labels. Self-supervised minimal labels post-training. Computational cost is very moderate for random forest, and it can be high to convolutional neural networks, but it's very high for the self-supervised. Interpretability, it's quite moderate and good for random forest. It's low to CNN, and it's very low for transformers as well. And so we probably would think that it's better to use supervised models where we have the labels when it's rich, and maybe self-supervised where we have scarce labels and we have a large scale application. Okay. So we are almost towards the end of the presentation. I just want to mention the importance of accuracy, validation, and bias, because in the end, maps are always just a model of reality, so they come with error. And inaccurate maps could lead to wrong statistics and to wrong policy if they are taken at face value with no investigation. So we need to validate. We need to compare maps with the ground truth in the end. And it's essential to maintain the credibility and reliability. So in this slide, basically, I've condensed the best practices, putting together the recommendation from Olofsson and from Sand-Bazar. And essentially, they are summarized in 4 key points. So design validation samples using probabilistic sampling, so that every location has a known chance of being selected, and this provides statistically sound accuracy estimates and support unbiased area estimation. Adjust the accuracy estimate by class area and report uncertainty. So we should calculate the area adjusted accuracy rather than relying only on the overall accuracy that we compute using confusion matrix, for instance. And we should also report the confidence intervals to reflect the uncertainty around the accuracy and the area estimates for each class. We should be able also to update validation dataset regularly. So we should refresh those samples, especially targeting areas where land cover change is likely, and combine random revisits and target revisits to balance cost and statistical rigor. And finally, validate and monitor stability across map versions, especially if we are producing a time series of maps, for instance, annual crop type maps. So we should perform a continuous validation with each new version of the map, but we should also monitor the stability of the accuracy over time across each product, so that then we can compare maps against each other. The good news is that on day 5 of the webinar, Dr. Sophie Bontemps from University of Louvain, she will explain in details methods for integrating Earth observation data with survey data and to account for error estimation. So we're going to have a very focused session on that. So I'd like to conclude with 6 brief takeaways from this first presentation. So we all, I think, can agree that EO data and AI are revolutionizing agricultural statistics. EO data offers scalable, consistent, and timely observations. AI instead is automatizing extraction of patterns from massive EO dataset. It's enabling unprecedented efficiency and granularity. And together they improve the accuracy, the timeliness, and spatial resolution of agricultural data. EO and AI can enhance, but will not replace ground surveys. At least this is the lessons learned working with many countries. Maybe I'm wrong, but I'm found believer of this. So EO, Earth observation, and AI are not a substitute for ground surveys. They are powerful enablers. They can optimize the survey design, they can guide efficient data collection, they can validate field observations, they can reduce cost in this sense, making agricultural statistics smarter, faster, and more robust. Accuracy and statistical validation are non-negotiable, meaning that pixel counts alone, they don't produce reliable statistics. So we need the statistical validation using probabilistic sampling, area-adjusted accuracy, and confidence intervals to each map. So in this way, we can generate credible, policy-relevant insights. And in this sense, Earth observation maps must be treated as model predictions, not as ground truth per se. Next, bias, data quality, and interoperability remain central challenges. So AI models, especially deep learning and those more, let's say, recent self-supervised approaches like the Presto, they bring, of course, tremendous potential, but also risks, because bias, complexity, and the black box behavior, which is very difficult to understand what's going on. So the regular validation, careful sampling, and monitoring model stability over time are really critical to mitigate those risks. And then a specific focus on the pre-trained and self-supervised models. They are currently now a game changer. So those pre-trained models, they drastically reduce the dependence on expensive label data, and they enable transfer learning across regions, scaling agricultural monitoring efforts globally, but demand rigorous assessment to ensure adaptability and fairness. And last, the future is really geospatial, intelligent, and inclusive. So a new era of agricultural statistics is emerging, one that is data-driven, geospatially enabled, and intelligence-powered. And building the future requires integrating Earth observation AI and traditional survey methods in a coherent, quality-assured system to leave no farmer or field behind. Thank you. Thank you very much. Paolo, would you like to moderate a session of question, or shall we move to the next step, to the next presentation? Thank you.
Thank you, Lorenzo. I think we can move to the next presentation as per the agenda, and then we go for the final discussion. So this next presentation is the update on the task team on the EO, right?
Okay, can you see the screen?
Yes, I can.
The presentation. Okay, thank you very much. So a very brief update on the UN task team. So first of all, we know the mandate. It's really about Earth observation integration with modern statistics, as recognized as a priority by the UN Statistical Commission, because we think that by this merging, we can have cost-effective, granular alternatives to traditional surveys and censuses. Initially, it started with the big data transformation sparked in 2014 by the Statistical Commission decision to establish of the UN CBD, so the Committee on Experts on Big Data and Data Science. And then there was the initial focus of this task team was to focus on satellite image under the Global Working Group, and they were targeting crop yield prediction through representative training data. Then we expanded the scope, so it was renamed Task Team on Earth Observation Data for Agricultural Statistics to encompass a broader range of Earth observation applications. Some milestones. 2017, we published a foundational guidance on Earth observation data use. It's called Satellite Imagery and Geospatial Data Task Team Report. 2020, we reconstructed restructuring led to the joint task team, UN CBD, merged with the UN SEAG, which is the Committee on Expert on Rural Statistics and Food Security, aligning Earth observation application with broader food security and agricultural statistics priorities. The most recent contributions are 2022, we released the lesson learned, a recommendation from selected Earth observation application on agriculture. 2023, we launched an Earth observation methodology knowledge assessment application to support capacity building. And last December 2024, we basically provided our report to the Committee of Experts on Big Data and Data Science, which then was integrated into the report to the UN Statistics Commission 2025. The team is composed by Ronald Janssen as a secretariat, Valérie Bizier as secretariat, Eduardo Vasquez as co-chair, and myself as co-chair. We are working in we have 13 active members, and then we have 3 new memberships, and then we also have 2 additional contributors. We also thrive on international partnerships, thanks to which we can then implement projects which really are providing the data, the information to the task team. So we collaborate, of course, with UN agencies such as the FAO, WMO, the World Bank, but also United States Department of Agriculture, the Asian Development Bank, the Digital Earth Africa. So there is quite a good international network. So what we are working on more in this recent time, in the light of the last 2004, is that we have, let's say, noticed some trends in the way we work. So there's been much more attention in fusion of multiple Earth observation sensors, both optical and radar data, very high resolution data, and agroclimatic data. We've moved more towards advanced machine learning and artificial intelligence. So being random forests, our benchmark and our, let's say, more reliable and tested approach, but more have started to use also different and experiment other approaches. In the last year also, we have had the introduction of the use and development of Earth observation data cubes. There has been a huge support by INPE in this, and in particular by Gilberto Camara, who has supported us in introducing this, but there are also other countries who are already actively using this. And then we have expanded our scope to crop yield forecasting models. So there was less of this in the previous report. So we've noticed that now more countries are coupling use of Earth observation data, AI, not just for the area estimation, but also for the production, for the yield. So fusion of multiple Earth observation sensors, we know that we know the benefit between optical and radar data. Essentially, optical only works during the daylight, but doesn't work when we have cloudy skies. Instead, the radar data works also during the night and works through the clouds. So together, this allows us to increase our time series data density, and essentially, so we can better describe the phenology of crops. And as of the last report to the UN Statistics Commission, we could see how different countries were using more or less data, but you can see almost every country now is using at least 2 sensors. And then we have cases like Brazil and Indonesia, and Poland, where we have 3 sensors, and Poland actually 4 sensors. So this is basically ongoing. And then we could see how the increased use of AI for essentially achieving effective temporal feature extraction, enhanced classification accuracy, robustness to noise and variability, computational efficiency, end-to-end learning capability, improved generalization of models, and versatile applications. And this is a bit of the type of algorithms that have been used more. But of course, you can see random forest is still, let's say, the winner. But then we have support vector machine. And now you can see CNN is also the third, let's say, most used one. I see that the time is running, so I want to leave some space for discussions. I just want to mention that the data cube, so the support from Brazil was very important to create training material and capacity building in other countries, in Africa as well as in Indonesia, for instance. So this has been a game changer to help countries to understand the difference from scattered EO data to analysis-ready data to regularized data cubes, and how these then inform much better our downstream applications. And finally, for the yield, crop yield forecasting, we've seen that there are some using statistical regressions, some are using machine learning, and some are using process-based models, and they all have they come with pros and contras, let's say. And in the last report to the Statistics Commission, Poland presented on machine learning. Right now, FAO is elaborating on a process-based model, so we will have some presentations soon during the next meeting. We've expanded the thematic scope of the team. So now we also consider disaster risk reduction, biodiversity, data governance, and we also have increased our collaboration with regional and global big data hub. And actually today's event and this series of webinars is the result of this increased collaboration. So I would just like to conclude also that the task team is now working collectively on the write-up of the UN handbook of remote sensing, but I don't have enough time to discuss on that. Or maybe Paolo, can I ask for your, because you're keeping the time, right? Do I have time to elaborate some slides on the handbook?
I think so, Lorenzo.
Okay, so one of the key new activity that was really thought in the last part of last year, in the summer, let's say, there was this initial energy profused by the UN Statistics Division and the global China global big data hub was really the idea of working on a UN handbook on remote sensing for agricultural statistics that would be really representative of the work of NSOs globally. And that would be really very practical in its approach and not just theoretic. So the work has started in theory last year with some initial meetings. Maybe some of you have already attended some of these. And currently it's unfolding. So I'd like to briefly present to you what will the book focus on, the structure, the current contributing authors, but also I want to let's say refresh the message that you're all invited to contribute. So if there is anyone who is interested, we would really welcome proposals. So the handbook essentially after initial meetings with the China hub and with the UN task team, has been agreed to be divided essentially in three main parts. And also some work has been done in defining roles and responsibilities and how to contribute to use cases and the timeline. For the outline of the book, we really want to keep theory and methods to the minimum required. So we want to provide this, but we think that this should be a handbook. So something that the user can use to replicate. And actually on this context, then we will elaborate on the structure of the book. So on the need for the user to be able to use immediately the contents of the book, we will see. The core of the book will be articulated on use cases. So an NSO has implemented crop type mapping in a specific year. This was the method, these were the results. And of course, which was the data used, which was the algorithm. And that's where the book then becomes different, because the idea is that for the author of that use case to make the code available to make the data available. And we will see how later. The third part of the book instead is on advanced topics. Those were topics that were considered now relevant, especially in line with the enlargement of the scope of the task team, so to disaster risk reduction, use of advanced AI models, and data governance. So going more into details about the various parts of the book. So currently the skeleton of the handbook is articulated on those chapters for part 1. So introduction, technical background, remote sensing images, optical and SAR, land cover and crop classification, quality control of training sets for agricultural statistics, machine learning classification of remote sensing images, uncertainty estimation and active learning in crop classification, accuracy assessment for agricultural classification using remote sensing, earth observation, big data sources and access. So all of those, except from the last one, are just theory. The last one is already providing instructions on how to access, because in theory, all of the following use cases should enable the user then to rerun those use cases. So it's important to know how to connect to the Earth observation big data platforms that are supporting this handbook. This handbook, of course, will be an electronic one. The second part of the book is focusing on use cases. So at this stage, this is the list, but as I mentioned, we are still open for proposals, so don't consider this written in stone. You are welcome to contribute and propose. So we're going to have a section on data collection and tools, a use case of data collection tools, use cases on remote sensing in the design of sampling frames, automatic extraction of parcels, fields of the world, crop type classification, crop monitoring with SAR images in Poland, crop classification in Mexico, multi-seasonal crop mapping in Senegal, crop classification using satellite image time series in Zimbabwe, crop classification land use mapping in Chile, crop yield estimation, early season crop yield mapping in Finland, rice paddy phenology in Indonesia, yield forecasting in Poland, rice phenology in Colombia. And finally, although we have less details here, we only have, let's say, the macro areas under the part 3, which is AI and advanced application for crop mapping. So probably self-learning algorithms will fall under this first category. And then we have application for drones and disaster monitoring, and then the data governance. So we have tentatively identified authors who could contribute here, but again, you're very welcome to step forward and be propositive. So far, the list of tentative contribute authors that have been contacted and preliminary have confirmed their availability. There are several of them. Some of them you already know them. So, for instance, we have Gilberto Camara, who is author, but is also the chief editor of the book. So he will be responsible for coordinating the inputs and to basically collate all of your inputs and make sure that the scripts are functioning. Then there are experts from the China Global Data Hub, Professor Pan Yazong and Professor Gao, we will see. We have Professor Pierre Deforny and Sophie Bontemps, who are quite acknowledged for their work on global and national crop type mapping from University of Louvain. We have Jan Nunes from IBG Brazil, and who will contribute with his work on the automatic extraction of parcel boundaries. Moving forward, we have colleagues from Poland, so Artur Laczynski and Przemysław Zlesiski from Poland. We have Abel Conorado from INEGI, Mexico, on crop classification in Mexico. Estefania Pizarro and Jonathan Paredes from INE Chile with the crop classification and land use mapping in Chile. And then we have colleagues from Finland on early season crop yield mapping. And then we have the colleagues from Indonesia, from BPS Indonesia, on rice paddy phenology. And again, we have the colleagues from Poland on yield forecasting. And then we have Freddy Martinez from Fedearos, and Yemi Montilla from DANE, Colombia, rice phenology in Colombia. And then we have colleagues from China, Li Quanzi and Huang Jingfeng on crop classification and yield estimation in China. Then we have a mixture of myself, Inbal Becker-Resche from NASA Harvest, Sophie Bontemps, from the extraction of crop statistics from maps. Unfortunately, Professor David Wepper is not able to contribute because they are too busy right now with this workload. So he tentatively proposed, but now he will not be able to contribute for this project. And then hopefully we will have contribution from the World Serial team on the Presto, on the global mapping, so the self-learning algorithms. And then again, we have colleagues from China, Zhang Jinshui and Maxing Ming on UAV applications, Professor Gauzi from China on disaster response. And hopefully, we are not sure though, because we have not confirmation yet. We were looking forward for contribution from Catherine Nakalembe and Guida and Gilberto on the data governance. We have to see about Catherine Nakalembe's availability. So how do we organize now the work? So essentially, we have articulated the work across different roles and responsibilities. So the experts in the NSOs and in the collaborating institutions with the task team contribute based on their voluntary intention, in line with their expertise and projects, particularly focused on real-world use cases and open data, because the caveat is that we should be able to contribute in the narrative, but then also share scripts and data that the user can run and reproduce the results. Then we have our chief editor, which is Gilberto Camara. Professor Gilberto is with us today, who will lead the writing and organizing the inputs. Then we have reviewers. We have 2 external reviewers who give guidance on the quality and direction of the book. Then there is a steering committee which resolves any disagreement or conflicting views. And then we have the UN support team, the IT team, who's coordinating the process and ensures smooth execution of tasks, but also the deployment of the actual electronic book on a server, the deployment of the scripts of Earth observation data, of field data on the UN global platform, so that those scripts can be run in a sandbox, and they are linked to the Earth observation data and to the field data required to run again that use case. So the main activities, final review of the skeleton and section proposal and assignments, those are already, let's say, finalized. And of course, we are now waiting for confirmation from experts about their acceptance of their willingness to contribute. So we are also open to new initiatives by authors who want to offer their contribution. And then, of course, we expect to review the inputs from the experts. Then there's going to be a feedback system to get back to the experts for clarification, and there's going to be the finalization and the publishing. And if we look at it more granularly, we can see that the work started in late 2024, and we are expecting to finish this by 2025 December. And in particular, right now, where we stand right now, we would like to receive all the authors' acceptance, so official commitment by the 15th of April. And this implies minimum of instructions, but maybe Gilberto is with us. He can also provide more details later on what is required in order to accept the invitation. By the 30th of July, the authors are expected to send the first draft of the chapter to the editor. By the 30th of August, the editor prepares the first version of a handbook and sends to the reviewers. And then by 30th of September, the editor and reviewers request corrections from the authors. By 30th of October, the authors sends the final version of the chapters to the editors, and by 15th of November, the editor prepares the first version of the handbook. How is the work coordinated? So in theory, we should have a bi-monthly technical meeting online, but it's also true that we can discuss these activities also during the task team on a monthly basis. But we've left this really to the flexibility and requirement of the editor, of the chief editor, to decide. We look forward to have one midterm meeting in June in Brazil, which will also be an intense hands-on writing of the handbook. And finally, we're supposed to have one in-person meeting in China in late 2025 for the launch of the handbook. Okay, this is all from my side. Thank you very much.
Thanks a lot, Lorenzo, for the presentation today. I'm going to start now the questions and answers session. And does anyone have a question or comment that want to share? Please feel free to go ahead. Lorenzo, I want to be the first one if anyone doesn't have a question. And my first question to you is, from your perspective, what are the biggest opportunities for using Earth observation and AI in agricultural statistics, specifically in Latin America? What do you think?
Thank you very much. I think it's a difficult question because it depends on the context, on the country. It depends on the let's say most urgent priorities. Definitely Earth observation data, like we could see in the first presentation, the main, let's say, by the end of the day, what Earth observation should be able to do is to make more efficient the workflows to produce agricultural statistics, meaning reducing the costs and increasing the quality, so increasing the accuracy. So based on this, you would think that you could expand this as much as possible to monitor the crops. So where are the crops being grown, being cultivated during the season? What is the area? And what is the expected yield? Now, on top of this foundation information, then you can build a series of applications for agriculture, okay, which are much more than just agricultural statistics. But the workflows required to produce accurate agricultural statistics, they are basically the pillars for the other applications. For instance, I give you an example. For the farmer subsidy or farmer compensation due to drought or due to flood or due to parasites, okay? Now the trend for Ministry of Agriculture is to use mobile apps through farmer registry, where the farmer is connected and he can send his request for compensation because he had a drought. Now, when in place in the country, when in a country you put in place a system that is able to monitor all of the parcels with accuracy, then you can use this information to inform policies and to inform the mechanism that validate the request of a farmer, for instance, for a compensation. So you reduce the need for auditing to go to the field and inspect if that farmer is correctly asking for the subsidy, because you also have to control for that. But more, let's say, on a larger view, you can actually inform policy on how to target their subsidy, which areas are producing more, which areas are producing less, and which areas would benefit from targeted subsidy. Because using those models, essentially, you are able to understand also the limiting factors of production. In some areas, for instance, nitrogen is not the limiting factor. So it's not about putting more fertilizer. But in some areas, for instance, you can see that the current business as usual is basically is affected by decreasing yields over time because of the climate change. So in those cases, you can use this type of information to simulate the production of a different variety. So a variety which is more resilient. So this is basically about resilience to climate change, adaptation. So you have many type of applications. For statistics, again, and I will conclude and leave the word to Gilberto, another straightforward application is using Earth observation data to inform the survey design. So you know where to go and collect in a much more precise way, because you have now maps of crops which you can use as stratification to allocate your samples. And as a bottom, basically as a result of this, you gain efficiency in your survey because you collect data that is more representative of the total population of agriculture, of crops. And you also can better manage your field operations because you know where to go basically to to uh, uh, um, to sample all of the different, let's say, subpopulation of crops within different agroecological zones. So you manage to better design your surveys. Thank you.
Thanks a lot, Lorenzo. We'll pass to Gilberto. Gilberto, good morning. Thank you for your presence today. I think you have your microphone muted.
Thank you very much. Okay. I'm going to be a little bit more specific in the case of Brazil. As you know, you have two types of census: the 10-yearly full census and the PAM and PPM, which is the municipal agricultural surveys, and the municipal I don't know the word in English, cattle pecuary survey. Now, I've worked with your data essentially from the 2006 census and then the PAM. And because of the ways the data is reported, because it's reported by farm, but say by farm, and we have big farms, and some of these farms cover different municipalities. So if you go, there is, for example, 29, at least from the 2006 census, there was 28 municipalities outside legal Amazonia that had cattle according to the PPM, but no pasture according to UBGE data. There are, so this is inside legal Amazonia. So you had this also in cropland. So you have some areas where the reported production area is up to 2 times, 1.7 times larger than the area of the municipality. So you have reports because of the way data is collected. There is the total area is correct, but not the location relative to the municipality upon which it's aggregated. And that's, of course, a situation where remote sensing data can help you a lot by producing estimates which are, let's say, spatially consistent in so which that you have the aggregation per productor, but you also have the distribution per municipality, which is not available in many situations. I have a detailed estimate here with many municipalities, which more production area reported by the PAM, the Municipal Agrarian Research Survey, then they have actual area. It's sort of very common. And it's only using remote sensing that you would be able to kind of address this problem. Thank you.
Thanks a lot, Gilberto. We have two questions on the chat. Not sure if If Lorenzo or Gilberto wants to address them. The first one is how can the small countries with limited resources start using AI without needing for large investments? And the other is for partnerships.
Great questions. So thank you, Maria Luisa, for those questions. So small countries with limited resources and in general, limited resources, let's say. There are ways to jumpstart Earth observation data by using currently freely available solutions, which may not be open, but are free. And this is the case of Google Earth Engine. So if you need to start to build technical capacity without an upfront investment, that's one way to do it, straightforward. There are also other initiatives which offer more, let's say, support and more computation power and more, let's say, independence from commercial products like Google, which are programs supported by international organizations like FAO, of course, but also space agencies. And then I connect, to the second part of the second question. There are agencies, for instance, European Space Agency. Let's make the case of European Space Agency. European Space Agency has programs that help scientists and non-profit initiatives to experiment, and it's called Network of Resources, NOR, Network of Resources. If you apply there, you explain your project, you say, I want to build capacity in my country and we want to test solutions. So for eligible projects, essentially, which is about sustainable development, it's about SDG development, really, you're going to get access to a cloud computing environment, a server that allows for computation, it allows for storage, free deployment of tools like Snap, for instance, which is the Sentinel-2 native application to pre-process satellite images, but you can also deploy your Jupyter notebooks. So you can basically decide which tools you want to use at free of cost. Just to mention an example, European Space Agency has awarded so far 2 times EUStat with, let's say, with network of resources sponsorized resources. So in one case, they provided us cloud space, cloud computing, and the access to the Sentinel-2 hub, essentially for a project in South Africa, Lesotho, to establish a national land cover monitoring system. And more recently, they granted EUStat $100,000 worth of satellite image commercial products for testing because of the project of rice mapping in Indonesia. So Indonesia realized that the freely available data from Sentinel-1, which is radar data, was not granular enough and not temporally dense enough to monitor the cycle of rice growth. So we applied through network of resource, asking, could we use Cosmos SkyMed, which is another product which is much more finer in space and in time. And of course, it comes with a cost. And then they said, okay, we would like to test this, but we don't want to pay upfront if we don't know if the data is good for us. So European Space Agency can make this happen. And there is also NASA. NASA also has a component for applying. And of course, the partnership then can also extend beyond the provision of resources, but also they provide for training. So I think partnering with the space agency is very important. And also for a more, let's say, long-term vision of the country use of Earth observation, space agencies, especially the national ones, first, they are launching their own satellites. So it's highly encouraged to use national products as much as possible because that should give you better results, but also ownership. And secondly, the National Space Agency in general, they also have a mandate to provide the cloud computing which allows you to connect and just get the data you want. So the famous data cube that we've mentioned during the presentation, having an agency in the country that can maintain that is a big, big advantage, because then when your team is going to be more mature and have all the scripts, you won't need to maintain the terabytes of remote sensing data. You just connect to it with your Jupyter notebook and you just get back your results. So that is another aspect of collaboration with space agencies in, I think, in the countries. Thank you. I think Gilberto wants to come in.
Yes, thank you, Lorenzo, for your important points.
Gilberto, we can't hear you. You are unmuted, but yeah, can you speak now?
Can you speak? Can I
Yes.
speak now?
Yes.
Okay.
Yes.
So the question actually begs another question. What exactly is limited resources? Because if I tell you that with $5,000, you can build a machine that can meet most of the needs of a small country. And with a little more than that, you can have a machine which meets the needs of reasonable mid-sized countries. Because your investment now should be purely on hardware. And I've just quoted yesterday a state-of-the-art machine with 8 terabytes Macintosh, with 64 gigabytes of memory, with neural net processor and so on. It's costing like $5,000. And I can do huge amount of things with that, because you can access all the Sentinel data, Sentinel-1, Sentinel-2, all the Landsat from lots of providers, download it, and there is software, open source software available, including done by Brazil, but of course others alternatives as well, that can allow you to do the work in your own laboratory. So when people think about this kind of thing, you don't have to maintain an archive of Landsat. You need to rely on Microsoft or Copernicus or whoever is providing this kind of data. You need to have the data. You need to know where to get the data at the moment you need and how to process the data to actively do the work you need. We're doing Brazil, the whole Brazil, with limited resources. Basically, one machine which costs in the cloud $2 an hour. So I think there is a misunderstanding about what is the entry cost for countries who want to do machine learning, reverse observation for agricultural statistics. The actual hardware cost is much, much smaller than the people. Orders of magnitude. Your problem is no longer, so your limited resources is essentially now, how can you, given that the hardware is so cheap, acquire level of, let's say, competence so that you reach a level of autonomy. This is really important, but for this, essentially, you are talking to the right man, because Lorenzo and FAO and EOSTAT is actually promoting this scope. So it's part of the testing, part of the work to ensure that there will be solutions available to countries, that they don't need to build huge services. They will have the intelligence needed to download whatever data they want, to use whatever data they want, at a minimal hardware cost, but at a significant, and I tell you, much more significant than anything, is the institutional intent. So if your institution wants to change, there are people like FAO, UN Statistical Division, who are willing to help. It's much more a question of institutional intent than limited resources. Resources in terms of hardware are not limited in this case.
Thanks a lot, Gilberto. We have more two questions, Lorenzo, on the chat.
Yes, I saw that. So there are two questions. So how can the information collected from unstructured crops be improved? So I guess that we're talking about unstructured crops, meaning areas where crops are intermixed, irregularly planted, or let's say they're not organized in clear homogeneous plots, like smallholder farming systems or agroforestry areas or mixed cropping. So how can we improve information collected from these areas? So there are a few strategies that are straightforward, which is the use of higher resolution imagery. So if 10 meters from Sentinel is not enough, and then we need to think of very high resolution imagery, PlanetScope, WorldView, Maxar, or even drones, which then can distinguish between closely planted mixed crops. And of course, it's a balance between resource availability and the need for accuracy. Time series analysis. So instead of working on single date images, monitoring the full phenological cycle, so the growth stage over time, which can help to capture subtle differences in the crop behavior, like when a plant green ups, greens, or when we have flowers, senescence. This might not be obvious if you just have one image. Of course, the assumption is that we have spatial resolution that is adequate to reflect the size of the crop, the mixed crops, okay? So temporal profiles like DVI, like EVI, they can be informative for complex systems. I would definitely think of fusion of different optical data. So Sentinel-2 with Sentinel-1, topological data, digital elevation model. Radar, for instance, can detect differences in crop structure and moisture that optical sensors can miss. And mixture of crops, they also come in, let's say, characteristics, habits of the farmer. So the radar can also help you identify the mixed crop structure that is typical of a specific combination. And I will get to that because that also refers to the type of how we define the classes. We will see that in a second when we talk about the AI. Then we can take action at the ground data collection, I think. So even limited reference data like photos from the ground, farmer surveys or mobile apps, which can improve the model training so that when you have a mixed crops, you have pictures of that and you add the image to the model. And then some crop specific probably knowledge as an expert. So having the agronomic parts of the equation put into the model. So which are the crops that are typically put together? What time of the year they're cropped? How do they look? This can improve the interpretation of the modeling. Now, the second question was what is the path, the best route for analysis and research using AI in the structured agricultural areas? Well, first of all, I mean, the foundation would always be that of working on a good data preparation of your labels. So trying to build a clean training data set with labeled examples, even if they are noisy, having some curated data is key. And having a lot of data, of course, is important. Even if it's noisy, it's better to have huge amount of data, even if you have noise. And then you can augment the data set. For example, you can include the images, satellite images under different conditions. So cloud cover, different phenological states, and so on. choice of the model. So you can start with convolutional neural networks for the spatial feature extraction. Then you can move to temporal convolutional neural networks, or temporal long short-term memory, or the transformer-based models like vision transformers and so on, adapted to time series. And you can capture how the crops evolve over time and see if you manage to discriminate those. There are like recent methods. There are like temporal fusion transformers, which are excellent at mixing structured and unstructured time series data for agriculture. So that could be another area to explore. And then I think the model inputs. So when you define your classes, you might also want to test the possibility, instead of having sharp structured classes. So for instance, I want to distinguish crop 1 from crop 2. So you have those rigid classes. You might also want to create new classes where you have a mixed class, which is based on probability, which means that in your mixed class number 1, you might say mixed class, it means that maize is 50% and 30% is sorghum and 20% is trees. So you can create those, let's say, probabilistically defined classes instead of having rigid classes. And this would be really a label smoothing and soft classification approach, okay? And of course, in the model, you would want to fuse the data. So like we said before, Sentinel-2, Sentinel-1, using all the polarization, vertical, horizontal. You could derive a digital elevation model features, slope, elevation, aspect, for instance. You may add rainfall and temperature data. I think, you know, the more data you have, and the better you are off with AI, and see if it managed basically to identify the patterns that describe your crops. Of course, by the end of the story, you should always try to work on uncertainty and quantification. So you want to predict uncertainty, and it's especially important for a structured area because you're going to have ambiguity, which is relatively higher than homogeneous areas. And then also using models to basically using methods to explain your models. You should be able to understand which bands, which features, even the dates of the features that the model is relying the most to predict, in order to see if it makes sense. And then, I don't know, maybe I would think of probably a loop, you know, that informs, and you rerun the model by adjusting features based on your feedback. Yeah, that's all I can think of on 2 feet. Thanks.
Thanks, Lorenzo. Gilberto is with a raised hand. Not sure if Gilberto wants to compliment.
I'm not managing to bring it down.
Oh, okay. We have 2 extra questions, and since we have a limited time, we have just 2 minutes. Okay, we're not taking more questions after those 2 ones. Okay.
Yeah. Okay, I'm going through the chat. So I see a question from Levindo Carloso Medeiros. Hello, Lorenzo. Is FAO working on the development of tools to evaluate training data set in office with the goal of building a publicly accessible global database? So we are, thank you for this question. So we have an initiative in FAO, which is EOSTAT, where we have collected a lot of field data. And of course, we would like to share this with the open community of scientists, of modelers, but we need to deal with the permission first from countries, because FAO collects data directly or indirectly in countries, but the data ownership is with the countries. So some countries are more straightforward in providing us authorization to redistribute. So for this reason, from the hundreds of thousands of data points that we have collected, we can really share just a few of them, which comes from countries which gave us basically green light. So probably having requests from NSOs, from scientists, for in situ data, that would help our cause in order to work more closely with countries to find agreements on sharing in situ data or part of the in situ data, and of course making sure that confidentiality, identification of the farmers, all of those, let's say, quite sensitive issues are managed properly. We also, I'd like also to mention that there is the World Serial, who is sharing to the public a platform for in situ data that they are collecting from surveys, from field survey. There is also data shared by FAO, in particular the VAPOR project on water productivity. So there are some, but these data sets are quite localized to irrigated crops. So it's really small irrigation plants, but still you might find there some data. But feel free to contact us, and then we see, based on your requirements, if we have data that can be shared. Other question from Weber da Silva Cavallo. Do you have projects that produce maps that monitor the growth of agricultural areas with deforestation in the world? So we are not working at global level, but we are working on national level on land cover and land cover change. So for instance, we have some projects in South Africa and in the I can think of South Africa right now, where we have a time series of national land cover maps where we can see the encroachment of agriculture in forest, but we have a forestry department in FAO, which are more interested instead in the FRA, which is the Forest Resource Assessment, which is a global process. So probably that falls more under the forest division. And then, okay, I think that's the end of the questions.
Thank you so much, Lorenzo and Gilberto, for the presentations and insights. I also want to say a big thank you to everyone who participated in our discussion today. The questions and comments that really enriched the conversation. So as we finish our first day, just a quick reminder, we have the links available for the concept notes, and I shared the links for the handbook on remote sensing, which is a reading for tomorrow. So tomorrow is an asynchronous day, so take your time to read the materials we mentioned. We hope you enjoyed the sessions today, and we will see you again on Wednesday at the same time, okay, for our next live session. Okay, have a great day, everyone, and happy reading, and see you again on Wednesday. Thank you.
Thank you.
Bye-bye, everyone.